Hi everyone, you are now watching the video presentation of the paper, The Gaussian Process Latent Autoregressive Model. As we all know, most regression problems have multiple outputs. For example, consider the problem of modeling the world's average CO2 level, temperature, and sea ice extent as a function of time t. It is reasonable to assume that temperature is a complicated function of both time and CO2 level. While sea ice can be modeled as a function of time t, CO2, and temperature, the original Gaussian process autoregressive regression model, GPAR, was developed to capture these functional dependencies in between outputs, where every function here is modeled by a Gaussian process with kernel both on input time t and previous outputs. However, there are two deficiencies in GPAR. First is that since the outputs from earlier dimension are directly used as inputs to the next function, noisy outputs result in noisy inputs to a subsequent stage. Secondly, GPAR does not handle missing values very well sometimes. To solve the first problem, a more principled approach is to do a fully Bayesian inference. Currently, observation y1 is used as input to y2 and y3. Instead of directly working on observations, we introduce latent variables, but approximation method is required to inference these variables. This method also enables non-Gaussian likelihood, such as classifications. We call this model GP Latent Autoregressive Model. GPLAR. For inference, we use ideas from the deep GP literature. By introducing inducing points to every layer, we get a lower bound for the log marginal likelihood. Posting a Gaussian form for each variational distribution, function f can be analytically marginalized out at each layer, and we utilize a nested simple Monte Carlo method to propagate hidden variables to the next posterior layer. When using a non-Gaussian likelihood, additional approximation is required. By maximizing the evidence lower bound, we jointly approximate the posterior distribution and the log marginal likelihood. Here is a simple synthetic data experiment result, where three outputs are drawn from synthetic GPs. We found that GPAR and GPLAR perform similarly when the observation noise is low. However, when the noise is large, as these results shown, many red test points and even black training points are not covered inside GPAR's error bars. GPAR can be overconfident and underestimate the uncertainty. On the other hand, GPLAR has well-calibrated uncertainty. For classification tasks, data are drawn from 4 synthetic GPs and the last 2 outputs are converted to binary outputs. This figure shows the last outputs with observation from 1 to 1.5 are missing. Note that 3 previous tasks, 2 continuous and 1 binary, help GPLAR to predict the last labeling task, while independent GPs fail to capture the dependencies and revert to prior distributions. The second problem of GPAR is that it does not handle missing values well on the first few outputs, since inference backwards are always harder than learning directly in a forward direction. We consider taking a deep GP analog of the bidirectional LSTM, and a deep GP structure running in reverse is added. The observations are produced by averaging the hidden variables at each layer and adding noise. Experiments on real-world data comparing bidirectional GPLAR, denoted by red dots, and single-direction GPAR, denoted by blue and purple crosses, have shown the former's superior with lower standard mean square error over all outputs regardless of ordering, especially when noise is significant. GPLAR also performs significantly better than independent GPs and deep GPs, denoted by brown triangles and green dots. We have also done experiments on non-time series real-world data, including radar images features and 2-dimensional latitude-longitude spatial point as input. Interested readers can refer to the following link for supplementary materials. Thank you for watching.